And good afternoon. My name is Chris White. I've been programming for about 30 years. I'm a demo scener, an open source developer, a toolsmith. I love to hack. Currently, I'm working on video capture and processing at D3 Engineering, which is a full-service outsourced product development company in the Rochester, New York, USA area. So I'm coming to you from the US Eastern Time Zone, where it is not quite lunchtime. We do, besides cameras, we do a wide variety of sensor work, and we work on Jetson and TI Jacinto and a number of other platforms. And we are one of the few NVIDIA preferred partners for cameras. The Jetson platform, for those who may not be familiar with it, is a line of Linux ARM64 system-on modules that have software compatibility up and down a range of performance and power levels. And they are all designed for edge computing and edge processing sort of applications. AI at the edge, running inference on trained models on live video data as it comes in, for example. And they have plenty of horsepower. NVIDIA does great GPUs, as you know. So they've got more than enough under the hood to take care of just about whatever you care to throw at them. And yes, somebody out there is right now thinking of the application that is too big to run on a Jetson, and that's okay. We can do those in the cloud. Some of the things that Jetson has been used for is network video recording and analyzing recorded video, optical inspection, mobile robot control. For example, Postmates has a little delivery robot that runs around the sidewalk that is powered by a Xavier, which is one of the higher end Jetson models. So we're here to talk about cameras. Let's talk about camera specifics. I'm delighted to report that you are not expected to memorize this entire diagram. This is the camera architecture for the Jetson, and it includes a lot of different options, particularly related to the onboard ISP for debayering and color correction and lots of other functions. Today, we're not talking about those. We're just talking about the V4L2 path, so we can focus on a little bit less of the stack. However, V4L2 is not the only technology we're covering today. When the sensor driver kicks off a video feed, V4L2 takes in the image data. We're going to talk about using CUDA today to process the image data on the GPU. And we're going to touch briefly on using EGL and OpenGL to display that image data. The focus is on V4L2 and CUDA today. EGL and OpenGL are nice because they get things out to a monitor. So here's the teaser. This is indeed the full source. Sorry, it's an image. It's not copyable text for a program that I wrote called D3 REQUEUE that takes the red, green, and blue pixels in a Bayer pattern from a Bayer camera and maps them over to the corresponding subpixels on an RGB monitor. The upshot of which is that you can view live video in color from a Bayer camera, even if you don't have an ISP configured to convert from this layout to an RGB monitor type layout. And by the way, are you able to see where my cursor is pointing? Let me know in the chat, please. If I wiggle the mouse, can you see it? No? Okay. All right. In that case, let's see here. How about this? Any better? Okay, there we go. Thank you. All right. So we're taking this pattern of camera, subpixels, 4 subpixels, mapping it over to a monitor. That's the use case. I'm sorry to say I was not able to get the technology together to do the live demonstration today, but I do have photographic evidence that it has happened. So we'll get to that at the end. I've tested this on a Xavier development kit with a D3 16-channel FPD link interface card. And yes, we can stream 16 cameras simultaneously into the Xavier. And the camera is a Sony IMX390. This particular one is a ruggedized module. It comes in a sealed case. And yes, these are marketing pictures, and here's what it actually looks like. So we've got the Xavier development kit on the bottom. 16-channel interface card on the top. I currently have 2 cameras connected, 2 cameras. And because the Xavier is a full Linux system, I HDMI and Ethernet, and there's a little USB for keyboard and mouse tucked under there. So it is very far from bare metal, but it's a very powerful platform. Okay, let's talk about the V4L2 subsystem a bit. V4L2 exposes the camera as a video device, Dev Video 0. But it turns out there's an awful lot under the hood, which I did not know when I started working on V4L2. Video 0 in the Jetson world actually corresponds to the Jetson's onboard video input component. It's a hardware block on the Jetson SOM system on module that actually takes care of getting video data to where applications can access it. That's a subdevice in V4L2 land. There's another subdevice for the CSI receiver. And then finally, way back at the beginning of the subdevice chain, we actually get to the sensor. Now, I ran this one on a machine with an AR0820 camera hooked up, but if I had run it more recently, would say IMX390. The subdevice architecture gives V4L2 a lot of flexibility. It is not just for cameras, it's also for display and all kinds of other real-time media applications that you might want to use. And this V4L2 stuff is not Jetson specific. This particular arrangement of subdevices is Jetson specific, but for what we're going to talk about interacting with Dev Video 0, that is not Jetson specific. Note that Jetson is currently on an older Linux kernel in the 4.9 series, so some of the details may have changed. If you're on the latest mainline, some of the I/O controls may look a little different, for example. V4L2 manages image frames in buffers. A buffer is just an area of memory where the frame is stored, and a timestamp, and maybe some other metadata depending on the specifics of the capture device. V4L2 buffers, if managed carefully, can permit you to schlep data around between applications or between the kernel and applications without having to copy it, which is key for performance because memory copies and the attendant memory bandwidth drain are a killer for performance. If you can avoid copies in a video processing system, you're doing well. I'm going to talk briefly about these 3 flavors just so you've heard the terms. These are the 3 kinds of buffers that V4L2 can handle. Different ones have different strengths and weaknesses. Not all applications will use the same combination. I happen to be using user pointer and DMA buff today, but in your application, use whatever combination meets your needs. In the case of mmap, the device driver allocates the memory, and then the application can map the device driver's memory into its own address space. For user pointer, the application allocates the memory and gives the driver a pointer to it. So you can allocate it any way you want, which we will see is very useful in this use case. And DMA buffs, in the case of DMA buffs, they are built to be shared within the kernel. So if you need to move memory between 2 drivers, DMA buffs are a good choice. All right, so controlling a V4L2 device. Everything that you do with a V4L2 capture device, a camera, is done with I/O control. So Dev Video 0 is like the tip of an iceberg, and it has a world of functionality underneath. No, you are not expected to know all of these I/O controls. There are a few key ones, and I'm going to break them down as we go through into a basic data flow. So this is the control flow of the application, and it matches the data flow of the buffers. Setup, queue some buffers, start streaming, DEQUEue, receive buffers, process the image data, and then requeue the buffers. And that is the main loop of the application. And when you're done, then stop. Okay. And I have a comment from Laurent that says user pointer is getting deprecated. Okay, well, that's too bad for me, but I guess it's good that Jetson is still on 4.9. Okay, so here we go. Like I said, we've got V4L2, CUDA, and EGL here. So I'm going to get a little bit of the CUDA and EGL setup out of the way first, and then we'll get into the V4L2 specifics. The CUDA API provided by NVIDIA gives you access to GPU processing functions and the ability to run arbitrary computations on a GPU. So you don't have to shove your data into a texture like you used to have to when using OpenGL to perform arbitrary computations. So we are going to create a CUDA stream, which will be a sequence of events that happen on the GPU. GPU and CPU run asynchronously, so the stream provides facilities for making successive GPU steps sequential and for syncing between the CPU and the GPU. Note, this presentation actually includes error checking code. The error checking code is not left as an exercise for the reader this time. It's important to keep the error checking code in. Don't try to leave it out. The driver is a state machine, and if your idea of the driver's state is different from its idea of its state, you will not get the results you expect. So lots of error checking code in this presentation. Okay, then the EGL setup. This slide doesn't actually say EGL on it. We'll get to that at the end. What we're doing here is we're using an NVIDIA provided multimedia API, MMAPI function to create a DMA buffer that we will render into. And the reason for DMA buffer here is twofold. One, I ripped it off shamelessly from an NVIDIA code sample. And two, the Jetson provides very easy facilities for mapping the contents of a DMA buffer into an OpenGL texture using EGL, and that's how we're ultimately going to get the image data out to the screen. Okay, just taking a look. Okay, so far, any burning questions? And let me know if I'm going too quickly or too slowly, please. And then, because the next thing we're going to dive into is all those I/O controls. All right, not seeing anything. Okay. V4L2, here we go. Oh, oh well, almost, sorry. This is the EGL part of the setup. I moved the slide earlier in the presentation so I wouldn't have to bounce around quite as much, but that change only happened about 5 minutes ago. In this particular case, we're rendering to an X window. We create a window that's a child of the root directly, so it doesn't have a frame or any fancy decorations, and create an EGL surface to go along with it. Then we can make a texture that we're going to use and tell EGL that this is where we're going to be rendering to. Okay, now V4L2. There we go. First thing you need to do when capturing with V4L2, regardless of what type of memory you're using, is to tell V4L2 and tell the driver to expect image buffers that it will be expected to fill with data. So here's our first I/O control. VidIOC rec buffs to request buffers. And these are video capture buffers of user pointer memory type, which we will see why on the next slide. We do this I/O control to tell the driver to get ready. In the case of mmap, it also causes the driver to allocate the memory. But here we're just saying time to get set up for user pointer based streaming. Like I said, it's a state machine. Make sure your application stays in sync with what the driver's doing. So here we allocate the buffers, and this is why we're using user pointer. Recent versions of CUDA, including those supported on Jetson, have this nifty function called CUDA malloc managed. In the Jetson architecture, there is no separate memory for the GPU. The GPU and the CPU have access to exactly the same memory. What that means is that you can actually allocate an area of memory that will be accessible from both. And this is very different from the way it used to be with discrete GPUs, where they had their own memory, the host had its own memory, the CPU, and you had to do bus copies to move memory back and to move information back and forth. So we are using CUDA malloc managed to get a pointer that the VI will be able to load image data into, and the GPU will be able to access easily for processing. And that's why we're using user pointer. And we stash these away in a vector just so that we can free them all later. Always clean up after yourself. Okay, now that we have buffers allocated, we need to queue them for the driver. So the way the V4L2 model works, for capture, we queue buffers to the driver. The driver then keeps that queue internally, and anytime it has a frame of image data, it fills the next buffer in the queue and makes it available to us. Since the driver needs to manage that queue, and we need to be able to control as the application how long that queue is and how much space is available based on our needs, we, the application, are the one to queue the buffers. So here, this is in a loop for not shown for all the buffers, and we use this QBuff IO control to stick one of the buffers that we allocated with its size into the driver's queue. All right. Now that we've queued the buffers, we can actually start the stream. This is about the easiest IO control of all. Stream on. That's it. We did tell it, once again, that it's a video capture stream as opposed to, say, a video display stream, but that's easy. This U-Sleep was in the sample I pulled this from, and it's not broken, so I haven't touched it. All right, time to wait for an image. You can wait for an image with select, poll, or ePoll. I'm using poll here because I like the API a little bit more than I like the select API. With poll, you set up initially what file descriptors you want to watch for. So here, CamFD is an open file descriptor to DevVideo0, and we are looking for input events. Now, in this particular sample, I also support pressing escape to exit. So we're also going to watch standard input for those. I'm not going to show that code because it's not relevant to today's topic, but that's why there's two file descriptors there. We poll, and note that we will abort on error. If poll returns 0, then we've timed out. It's been 5 seconds and no frames have come through. And on Jetson, generally speaking, when you have a timeout, your best bet is usually to stop and restart streaming. If we did not get a timeout, then something has happened. So we can see what it is. All right. Poll fills in the R events member of this structure. And poll in is input event, what we were looking for. So if we have gotten an input event, if the DevVideo0 file descriptor indicates that it is ready for read, that doesn't mean we actually call read on it. It means we call IO control yet again, but it means that there's a buffer available that we can pull out of the driver's queue to do something with. So here we go. Video capture, user pointer, same things, you see them over and over again, and here's DEQUEue IO control. So we give it the pointer to our buffer structure, and it will fill in the user pointer. Since these are user pointer buffers, once we have successfully dequeued a buffer, we have a complete image frame, and its data lives in this user pointer, which we happen to know is a CUDA managed memory pointer. Okay. This side of the screen over here has the chat on it, so that's what I'm looking at every so often. All right, so now we are ready to process an image. This is, I said that stream on was the easiest IO control. Here's the easiest part of all the plumbing. That user pointer, because it's managed memory, is already a valid pointer for use by GPU code. So we don't technically have to do anything. We could just send that user pointer into the GPU, and the GPU would crunch merrily away on it. For the sake of performance, we're using this call stream attach mem async. Stream attach mem async tells the memory subsystem in the Jetson that the GPU is now going to be crunching away on this for a while, as opposed to the CPU. Excuse me. Sorry. So the memory subsystem arranges its caching so that the GPU will have ready access to that image data. Again, optional, but strongly recommended for performance. Okay, more plumbing. All right, so now that's all for the input frame, but we still need to connect the GPU code that we're going to run to the output frame. Remember, the goal here is to use the GPU to convert that RGB Bayer pattern into RGB, 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 suitable for display on a monitor. So we earlier created our DMA buff file descriptor for the output buffer, and we created the EGL display and surface that we were going to use to bridge that file descriptor over to the OpenGL world for rendering. So here, this is another MMAPI function. The DMA buff is represented by a file descriptor, and we map it over to an EGL image, which is a handle. It's a cookie. Then, that's not quite enough for the GPU. So for the GPU, we register that EGL image to get a graphics resource. And then, once we've gotten that graphics resource and CUDA knows that this EGL frame exists, then we tell CUDA, okay, now that you know about this frame, actually, yes, I really do want to process into it. So that's what this graphics resource get mapped EGL frame is for. And the resulting CU EGL frame structure includes, among other things, a GPU device pointer to the memory of the DMA buff. Okay. At the end of all that, we do a context synchronize to make sure that everything that's gone before has completed and we're ready to run the frame on the GPU. Finally, CUDA. So this is where we actually do the processing. If you've not seen this syntax before, you're not alone. CUDA is an extension to C++ that adds, CUDA is a lot of things. One of those things is an extension to C++ that adds this syntax for launching a kernel, which is to say calling a function on the GPU. So what this is going to do is call a function called Bayer16 to ARGB32. We give it our user pointer, that was a device pointer, to the source data. And here's the device pointer to the mapped EGL DMA buffer output frame. So there's our parameters. Now this stuff in the middle, grid size in blocks and block size in threads. Okay. The way CUDA breaks down GPU operations is by running the same function multiple times in parallel, in massively parallel scale. And the parallelism is managed at the block level, where you have a number of threads that are all executing the same code in lockstep, and then the grid level, where you have multiple blocks. And these are described in 1D, 2D, or 3D terms so that you can map the size of block and grid that you want to the size of your image or to whatever your problem space may be. If you're doing 3D tensors, you might want 3D blocks, or maybe you want a 2D grid of 3D blocks, lots of options. In this particular case, I picked a 64 across by 1 high block. So each block is part of a row. And then for my full image, that gives me 30 blocks across and 1080 rows down. So I've sliced up my image into these little pieces, and the GPU can work on at least all of one little piece at the same time. And in reality, it will be working on many more than just one of those blocks at a time. Here's what that function that's getting done 64 times here and 64 times here, all in lockstep. Here's what that function looks like. This is not the full rebayer function because I need to not show you an eye chart of source code. That would not be helpful. So I just did a simpler one where I stuff the pixels value, the high 8 bits of the pixels value, into the bottom channel, the blue channel of the monitor pixel. This global keyword is your clue that this is a GPU function. In fact, that is what denotes that this is a GPU function and not a function that's going to run on the CPU. It takes parameters, same way as any function does. But it also has some other things in scope. It has these magic globals called block index, block dim, and thread index. These are vector, these are vec2, vec3. They have X, Y, Z members. And they tell you the size and position of this block. So here, blockdim.x is 64, and blockdim.y is 1, because we've got these 64 by 1 blocks. Thread index is where we are in that block, 0, 1, 2, 3, up to 63. And thread index y will always be 0, because I set up the blocks that way. And then block index is within the grid, 0, 1, 2, and then going in y, 0, 1, 2, and so forth, down to 1079. So this little incantation, or something like it, exists at the beginning of every CUDA function, essentially, to let you know which part of the data you're supposed to be touching. The parameters to the kernel launch, the parameters to the function call, are the images as a whole, not where in the image you are. So these magic globals are how you find out which data you're supposed to be crunching right now. And global parameters there, and then these magically in scope vectors that show you where you are. So here, I also passed in columns out and rows out parameters to say how big the destination image is. Check and make sure before you do processing that you're still within range. Because if, for example, if the size of the image were not a multiple of 64, there would be one block where some of the threads would be writing past the end of memory. And that's a seg fault, just like it is on a CPU. And when a CUDA kernel seg faults, in my experience on Jetson, you usually get a dull green flat field if you're dealing with YUV data. So here we are. If we are within range and the destination memory actually exists, finally do something. And in this case, the something is, like I said, just to copy the top 8 bits of the source into the corresponding pixel of the destination. And in the case of REQUEUE, the additional complexity is to look at the color filter array pattern and say, even, we've got this is green, let's say in green, green and green, there we go. So if we're on an even column and an even row, it's green. If we're in an odd column and an odd row, it's blue. Odd column, even row, red, anyway. So that's the additional complexity in REQUEUE. Okay, I'm gonna stop there for just a moment, and there's a question. Can the GPU function read source data outside of the block or thread? For instance, when an output pixel depends on its neighbors. Absolutely. You have access to the full source and destination array here, and you can read and write anywhere you want. There are patterns that are faster and patterns that are slower. So when you're writing a function like this, if each pixel is totally independent of the others, then that's the fastest. If each pixel accesses other pixels that are at a fixed offset, so you kind of step through this way, then that will also be pretty fast. If you're actually doing honest-to-goodness random access, that will not be fast because the GPU will always be trying to pull dirty cache lines from its data cache, or data that's not in its data cache already. So there's a lot of, we can talk more about that if you want, but there's lots of different speed tricks that you can do to try to get the data as quickly as possible. And I will say one of the reasons for the block versus grid division is that you can share data very quickly within a block. It's slower from one block to the next block. So if you're doing like macro blocks, if you're doing JPEG or something, some kind of compression that uses macro blocks, and you can set it up so that your block size on the GPU includes everything you need to compute one macro block of the output, you can very quickly access within that block and generate the output pixels. Also worth mentioning that in this particular case, I'm doing pixels to pixels, but because this is essentially an arbitrary function call, it doesn't have to be pixel data. It could be, we could be running a transformer neural network on this, and we could be taking in strings of ASCII and outputting strings of UTF-8 in another language or something. It doesn't have to be images. That's just what we're talking about today. Okay, any other questions at the moment? Not seeing any. If you're typing at the moment, I'll come back to them and catch up in a minute. Okay, cleanup. Definitely remember to clean up. If you don't clean up, you will eventually run out of resources and your program will die. So here we are unregistering the resource that represented the destination frame. And in this particular case, we create and destroy an EGL image every frame. I haven't actually tried whether I could use one EGL image over and over again because I haven't needed the speed. This is just an image display tool. But that's something that I would investigate if I needed more speed. Okay, rendering to the display. This is OpenGL stuff now. We have a very basic vector and fragment shader pair, a shader program that calls the OpenGL texture 2D built-in function to pull data for that pixel from a texture variable defined as this sampler external OES. And sampler external OES is an OpenGL extension type that can be hooked into these EGL images representing DMA buffs. And here's how we do that. Get the EGL image like we did before, bind the texture that we created earlier, use texture target to connect that texture ID with that EGL image. And then there's a call that I didn't show that sets up the coordinates for, two big triangles. And then this call draws those two triangles. And when the fragment shader runs, each pixel goes into the texture, which is actually this EGL image, which is actually this DMA buff, pulls out the output pixel, drops it on the screen. Very quick. Okay, that's the end of the processing part. Now, going back to V4L2. Now we're back to V4L2 land. We've done all this CUDA stuff and EGL stuff and everything. We are done with one frame of the image. Like I said, the V4L2 driver has a queue of buffers, and the application is responsible for managing that queue so that the application has control over what's going on. So when we're done with a buffer, we re-queue it back to the driver with this QBuff IO control. And we didn't change any of the V4L2 buff structure since we last dequeued it, so we can just re-queue it right back. Again, this is a user pointer buffer. It's got that M user pointer member. Goes back in the queue. And next time we dequeue, we'll get another buffer from somewhere else in the queue. Okay, so we stream for a while, and when you hit escape or timeout or whatever your stop condition is, time to shut down. Stream off is just as easy as stream on. This is a video capture, and we're done. Doop. There we go. And then clean up after yourself. Free all of the user pointer buffers that we created, and destroy the DMA buffer that was used for the output. And because we've been cleaning up each frame as we go, we don't need to also destroy EGL images or things. We already did that. This is the state that's persisted across the duration of the capture session. And that is actually it. So we set up our CUDA and EGL and OpenGL stuff. We set up V4L2 by calling REQBuffs, IO control REQBuffs, to request buffers. We used CUDA malloc managed to allocate the space that our source images were going to come into. And we used QBuff on Dev Video 0 to put those buffers into the driver's queue for use. We said stream on, vidIOC stream on to start the stream. We waited using poll for the driver to let us know that there was a frame ready. And when the frame was ready, we called the IO control DEQUEUE to get the head of the driver's queue full of image data. We did all the crazy plumbing to make sure that the destination was accessible to CUDA, and we told the memory subsystem to cache our source image for fast GPU access. Then we ran our CUDA kernel, and that went over the whole image in these parallel blocks, did the copy, and it could have done whatever we wanted. When we were done, we requeued the buffer back to the V4L2 driver, and we did that live, real time. And when we were done, we said stream off to stop the stream. And this is, like I said, there's photographic evidence. This is a raw image captured by REQUEUE, actually dumped to disk and viewed in VUIA. And because there's no debayering, unless you know something about the color filter pattern, you just get a monochrome image. And this is a cell phone picture of the monitor showing REQUEUE actually running, and that it is indeed colorizing those, it is indeed interpreting that color filter pattern and colorizing appropriately. And so we get the colors on the color checker. And yes, those are the right colors, just in case you're wondering. Thank you very much, everyone, for attending. I'm going to look at the chat for a moment. No other questions at present. I'd like to thank the conference organizers for having me. This has been a lot of fun. It's been fun to prepare and fun to present. I'd like to thank NVIDIA for, of course, inventing Jetson, for the figures, the Jetson family figure, and the camera subsystem diagram that we used, and for a lot of the sample code. REQUEUE is some code that I wrote and a lot of code that I cribbed from different places to get all of the events into the right sequence to actually be able to accomplish the task. I'd like to thank Jerome, Kelly, Jason, Reese, Kathy, and Ellen for their contributions to the presentation. I'd like to thank my employer, D3 Engineering, for giving me time to work on it. And I'd especially like to thank all of you for attending. If you'd like more information, first of all, these slides will be available after the presentation, once I have a chance to run a PDF. So in the coming days, there will be a PDF of these. Here's some links for you. This is the kernel documentation, and remember, Jetson is a little older, so you might, if you change this to the appropriate version for your version of Linux. But that's the subsection about capture devices. On Jetson, the MMAPI, which provides all of those NV buffer and EGL type functions, that's its documentation page. Lots of good stuff there. I will add a CUDA link before I run the PDF of these slides, which I just realized I did not include. There's D3 Engineering, d3engineering.com, and there's my email and LinkedIn. Be happy to connect and talk further. Thanks very much. I am, in my mind, imagining the wild applause of the masses. All right, questions. Is the full application code available somewhere? Unfortunately not. D3 has not yet made a determination on whether it is going to release or commercialize D3 REQUEUE. So unfortunately, the full source is not available. Sorry about that. My pleasure, Matthew, Trevor. My pleasure. Other questions, comments? And we have a little time, so I can let you get to your lunch or dinner sooner, or I can talk about more stuff. Up to you. Looking at the chat, I'm also going to check the Slack channel for just a moment to see if there was anything in the Slack channel. Not that I can see. Question from Kieran, am I debayering or presenting the RGB as individual RGB pixels? Good question. I am not debayering. Let's go way back. Here we go. I am pulling out, I'm taking the raw value. So these are just 4 numbers. And if you don't know what the color filter array pattern is, you don't know what they represent. I have REQUEUE programmed to know various color filter patterns based on the V4L2 pixel format. And it takes the red value and stuffs it in the red pixel, subpixel, and zeroes out green and blue here. And similarly for the green, it zeroes out the red and the blue channels. The V4L2 pixel format enumeration has different options for all the different color patterns, whether the red is here or here, whether the greens are this way or this way. So you do get that information from the V4L2 driver, with get another I/O control to ask for the device's capabilities. And then I have some LUT and some sort of semi-optimized special cased code for the different patterns to handle them, each of them appropriately. Good question. Yes, it is showing what the raw image looks like on an RGB display. Yep, and on this one, green and blue are 0, but if I had made them black, you wouldn't have been able to see the line between them. So yes, the blue and green subpixels here are 0, and here the red and green subpixels are 0. And this tool, I originally wrote this tool actually for my own use. I was bringing up a camera. This is one thing that D3 does regularly. We write camera drivers for new cameras. And these are generally industrial type cameras. These are not usually webcams or Raspberry Pi cameras. But I was writing a sensor driver, and I had V4L2 streaming. And on Jetson, remember, we've got all these other pieces of the puzzle. So all these green pieces here that I didn't talk about, getting a driver to stream this does not mean that that driver will necessarily stream with all the rest, and particularly does not necessarily mean that it will stream with the ISP. There's usually an extra step after streaming with V4L2 to be able to stream the ISP, and D3 does this all day, every day. So we've been there. We have a lot of experience. If you need help with that, please call us, because it is not trivial. So I had a sensor driver. It streamed V4L2 just fine, but it did not yet stream through the ISP with libargus is the name of the library that interfaces with the ISP. So I wrote REQUEUE just so that I could see what the camera was producing in some kind of color, and make sure that I had the color filter array pattern right, for example. On one notable occasion, I took a picture of a Coca-Cola sign. Here we go. On one notable occasion, this was blue, bright blue, because I had gotten the color filter array pattern wrong in the driver. So I flipped it around and it turned back red, and life was much better. But yes, this is one of my test targets. So I wanted to see the colors on the screen even before I had debayering through the ISP. So I wrote REQUEUE to show me this simulated color display. And it has actually proved to be useful in a wide variety of applications, including some customer applications. Oh, I'm still sharing the screen. Thank you, Trevor. The same exercise, so I will show you in a moment. Let's see, I'm going to stop sharing for now here. Here we go. All right, camera now. This is one of my test targets. And it's a Coca-Cola sign with a nice bright red and white Coca-Cola logo. And it came out, there we go. And this part was all blue. This was green, this was white, but this was all blue because I had gotten the color filter array pattern backwards in the driver. So that's why I wanted to write REQUEUE. Okay. Would the same exercise be possible with OpenCL? Yes, the same exercise would be possible on OpenCL, but I do not believe there's OpenCL support for Jetson currently, which is perhaps not a surprise since CUDA and OpenCL are in many ways competitors, and NVIDIA is the originator of CUDA. So for Jetson, I would definitely stick with CUDA. But yes, the same flow on other platforms. All of the V4L2 flow would be the same. I have not done much OpenCL myself, so I don't know the specifics of what buffer types you would use and how you'd map them in and out of the OpenCL kernel's space. But the V4L2 stuff should all be the same. And yes, faking textures and sampling them manually. So we have Kieran says they have an OpenGL debayer. That's awesome. I would love to write a GPU ISP sometime. That would be a lot of fun. And Laurent, in your presentation earlier, if this is the same Laurent, I can't tell on the screen. I saw that you were mentioning GPU ISP as something that might be interesting in the context of libcamera, and that would be awesome. GLES shaders. Yes, it is painful to fake textures and sample them manually. you can do it. You can even do it for audio data. I've done it for audio data on ShaderToy. I wrote a software synthesizer for drum beats that rendered audio data into a texture, which ShaderToy then unpacks out of a texture back into a linear audio buffer and pumps out the speakers. So yes, CUDA is much nicer in that respect. Okay, other questions or comments? I do appreciate the interaction. Going once. Oh, and let me check Slack one more time. Don't see anything else on Slack. So thank you very much, everyone. You get to go to lunch or dinner early. It's been a great conference. Thanks very much, and I really appreciate it. Hope to talk with some of you more afterwards. Please do send me an email or hit me up on LinkedIn if you have any feedback on this presentation. I'd like to know how I can improve. Thanks very much, everyone. It's been great. Have a good rest of your day.